So welcome back guys, and I do hope you and your family are doing really well. We're going to do a required practical today, or at least I'm going to do it, and you're going to work with some of the data that I gather. So this is a required practical. It's how does the length of a piece of wire affect its resistance? So how does the length of a piece of wire affect its resistance? Well, cutting straight to the chase, I guess it's pretty obvious that if a piece of wire doesn't conduct electricity very well and you've got a short length of it, then if we put more and more and more wire in a line in series, we have a longer piece of wire, then there's more bad conductor, so the resistance should go up. And that's correct, obviously. But as with all things in physics, it's not quite as simple as that. So I've drawn a little circuit here just to show you what we're going to do. We've got a normal battery, we've got a wire, normal wire coming down, and then we've got a piece of wire that we're interested in, and it's going to be taped onto a meter ruler. So what that means is we can measure different lengths. And I've got a sliding sort of contact here, and I can press it on at different lengths of wire, 10 centimetres, 20, 30, 40, and I can measure the current for those different lengths. I also need to be able to measure the potential difference, the voltage, so I'm going to put a voltmeter across the circuit. There it is. Okay. And if you look at that carefully, you'll notice that we've got the voltmeter measuring the voltage between here and here. Okay. In fact, it's really only over just that bit of wire there because the other wires are really good conductors. It's also measuring the potential difference of the battery. So we've got the pressure, the voltage across the bit of wire, and we've got the current flowing through it for this length. So if I move the slider along, we're going to measure the current for different lengths. And then if you remember, resistance is potential difference in volts divided by current. And we can see what's the resistance like at 10 centimetres, 20, 30, 40, 50, etc. and see how does the length affect the resistance. So what I'm going to do now is I'm going to take the camera around to the apparatus and show you how I do the experiment. We'll get some data and then you can graph that data, and we'll come back and talk about the results that we got. Great, so here's the apparatus. It's a bit difficult to get into shot because it's quite long. So what we've got is a meter ruler with a piece of wire on it. So that's the wire we're interested in. And this wire has resistance. It's not a very good conductor. Okay. The other wires we can completely forget about their length because they're made of copper and they're really good conductors. I've got a voltmeter measuring the potential difference of the power supply, and that will be the voltage that we put across our section of wire. And I've got an ammeter to measure how many amps are going to flow when we connect it. And here's my connector. Okay. And I can connect in two ways. I can connect in by touching with a normal wire, which has quite a large surface area, or I can use a jockey key. Think of riding on the wire, jockey key. And this has got a knife edge on it, a very sharp edge, and I can use that to connect in as well. And think of the difference there, okay? A very, very small point of contact, quite a wide one, okay? So what you do with this apparatus is get it set up like this, and you touch on at 10 centimetres, read the potential difference and the current, 20, 30, 40, 50, 60, etc. Right the way up to the full meter if you want. And then you plot a graph of the data you've got, and I'll do that on the board with you in a minute. And then you need to see what you think happens to the resistance. Now, the graph we're going to plot is a graph of resistance and length. Okay, we're not plotting volts and amps, current, or plotting potential difference and current. Okay, what we're going to do here is we're going to use the voltage and the current to work out the resistance, and then when we've worked out the resistance, we're going to plot a graph of at a specific length on the x-axis, what's the resistance, at the next length, what's the resistance, and then when we get that graph, we'll explain why it's the shape that it is. Okay, so time to look at our data. So the plan was for you to work out the resistances. So you took all of your voltage values and your current values, and you divided the voltage by the current, the potential difference by the current, and got a resistance for each length. Then plot a graph, and this graph will have the independent variable, the one we know, so that's length in centimetres on that axis, and it will have the one we didn't know, the dependent variable, resistance in ohms on that axis. Okay, and what you normally get is a pretty straight line. Okay, so if you get a straight line going straight up like that, it's obvious that as the wire gets longer and longer and longer, the resistance gets higher. For every centimetre, you might gain 1 ohm, you might. So 2 centimetres, 2 ohms, 3 centimetres, 3 ohms. It's a relationship that's directly proportional. But in fact, when you do this in a school lab, sometimes you get a slightly weird effect. You get the graph sort of goes sort of up to begin with, and then sort of goes straight. Okay, it depends on what numbers you put on the axes to how this forms. Okay, now I'm pointing out that this bit here is straight, it's linear, and this bit is slightly curvy. Okay, now that's complicated. So let's just try and explain what's happening here, or more importantly, can you see what you actually visually see on this graph? What's it telling you? Well, it's telling you at very small lengths, the resistance grows quite quickly for every centimetre you increase. And then when you get to quite a small length, but a length nonetheless, the resistance grows evenly with length. That's proportional, or a linear relationship, and this isn't. There's a little bit of curvature, a little bit of resistance kind of growing quite high at the beginning. Okay, and there's a reason for that. Yeah, the reason that the resistance is a little bit higher than you'd expect at the beginning, okay, is because when you put the jockey key on, the wire has a current passing through it, quite a lot of current, because it's a short piece of wire, a low resistance, and the wire will get hot. And if you remember from the filament lamp, you're not controlling the variables then, and if the wire gets hot, then its atoms vibrate a bit more, and if the atoms vibrate a bit more, the resistance increases slightly more rapidly than you'd expect. Now that's taking it a bit far. Okay, at GCSE I would generally expect you to get a straight line, and you'd say as the wire gets longer, the resistance goes up, and if you double the length of the wire, you double the resistance. It's kind of a proportional relationship. But just occasionally they ask you for a few sort of safety issues and things like that. So we're using low currents and low voltages, so they're safe, we're not going to get electrocuted. The only safety issue with this one is down here, when you use very, very low lengths of wire. You might then get a high current, you're not going to electrocute yourself, but what you could do if you touched the wire or left it on for any period of time is you could burn yourself. You get a little line on your finger where the hot wire is sort of burnt into your skin. So that's something to be aware of. So if you want a straight line graph with this, you touch it, take a reading, take it off. Touch it, take a reading, take it off. You do it quickly. You don't leave it connected for ages and allow it to get hot. Okay, so I hope you've got a reasonably good understanding of the experiment you did, but there's one thing we missed. Do you remember I said we could use the jockey key, which is very pointed, or we could use the end of a wire, which is quite wide? Okay, so give a little bit of thought to what the problem is there. It's actually fairly obvious. Yeah, the student that uses the jockey key gets a very precise position on the wire. There's a better measurement of the length. Whereas if you use a normal plug, yeah, the connection is much wider, and it could be one side of the connector or the other side or the middle. You're not connecting at an exactly or well-known length. You're not getting such a precise measurement for length. So occasionally they say, what improvements could you do with this experiment? Well, one of the improvements is, if the student uses just a wide lead, use a sharp point. You might not remember the term jockey key, but use a sharp point to give you a very clear position on the ruler of the length of the wire you measured. Anyway, that's required practical. Bit of a rush, I know, but that's the situation we're in at the moment. Anyway, I hope you found that useful, and I look forward to seeing you for another lesson before too long.